History records a single individual capable of deciphering an ancient Egyptian language, mapping the cellular receptors in the eye to explain color vision, and deriving the mathematical formula for the elasticity of solid materials. Thomas Young achieved all of this alone. A Quaker child prodigy, he mastered 14 languages by age 14 and operated entirely outside the traditional academic boundaries of the late 1700s. When Napoleon's army unearthed the Rosetta Stone, scholars could not translate a single symbol. Young applied his linguistic pattern recognition to the artifact, identifying phonetic bridges between the Greek text and the previously indecipherable hieroglyphs. He spent his professional life as a physician. During his clinical work, he demonstrated that the human retina relies on exactly 3 distinct receptors, red, green, and violet, to process the visible spectrum. Because he ignored the narrow specializations of his peers, Young became known as the last man who knew everything. This cross-disciplinary intellect gave him the tools required to address the most stubborn physics mystery of his era. By the early 1800s, physics faced a single unresolved question: what actually is light? This is the title page of Isaac Newton's Optics, published in 1704. In it, Newton argued that light was corpuscular, declaring it was made of tiny, discrete particles traveling in perfectly straight lines. Newton's influence dominated British science for over a century. His particle theory was taught as absolute fact, and questioning it meant risking one's professional reputation. But Young's observations of sound waves in air and ripples in water didn't match the behavior of particles. He noticed that waves could overlap and bend in ways Newton's corpuscles simply could not. Young suspected the foundations of classical optics were flawed. He set out to challenge the scientific consensus using nothing more than the physics of a water puddle. Young proposed that light is not a stream of physical bullets, but a wave undulating through a medium, identical in behavior to sound. He relied on a mechanic called interference. When 2 waves overlap in perfect rhythm, they amplify into constructive interference. But if they shift out of sync, the forces cancel out completely, leaving a flat line, destructive interference. If light behaves as a wave, adding one beam of light to another could theoretically result in absolute darkness. To prove this to a skeptical Newtonian establishment, Young designed an experiment intended to provide physical results that could not be interpreted as anything other than wave motion. This diagram outlines Young's 1803 experiment. A sunbeam enters a tiny pinhole and is split by a narrow card into 2 diverging paths. Newton's particle theory predicted this would result in 2 distinct, hard-edged bands of light. Young observed something different: a wide pattern of multiple bright lines separated by bands of pure darkness. These dark spots are destructive interference in physical form. They are the locations where light waves from both sides of the card met and canceled each other out. Using a ray of sunlight and a piece of paper, Young demonstrated that Newton's particles did not exist. Light was a wave. The British scientific establishment met Young's 1803 presentation with ridicule. They mocked his methods and dismissed his evidence to protect the Newtonian consensus. The backlash was severe enough that Young began publishing his physics papers anonymously. He feared that if his patients associated him with scientific heresy, his medical practice would collapse. Decades later, scientists like Augustin Jean Fresnel and James Clerk Maxwell validated Young's work. They expanded his interference principle into the foundation of electromagnetism, shown here in the perpendicular vibrations of electric and magnetic fields. Physical evidence eventually overcame institutional authority. The particle model was buried, and the wave theory became the new standard of physics. In 1905, Albert Einstein proved light behaves as both a wave and a particle simultaneously, a concept known as wave-particle duality. Yet, even with our modern understanding of quantum physics, Young's 1803 setup remains the standard laboratory test for observing quantum behavior. Physicist Richard Feynman later observed that the double-slit experiment contains the only mystery and the very heart of quantum mechanics. Young transformed our understanding of the universe because he refused to specialize. His ability to connect linguistic patterns, ocular anatomy, and fluid dynamics allowed him to detect the wave structures that govern physical reality.
For centuries, the ultimate goal of Western science and philosophy was to achieve a perfectly detached, God's-eye view of the universe. The Cartesian Hegelian ideal assumed that reality was a giant predictable machine, and the best way to understand it was to remove the observer entirely from the equation. Under this framework, true rationality required erasing your own perspective. The closer you could get to absolute objectivity, looking at the world from nowhere in particular, the closer you were to the truth. In 1843, the Danish philosopher Søren Kierkegaard published Either-Or. Modern analysis by physicist Hans Halvorsen reveals this text as a targeted teardown of the Enlightenment's obsession with absolute objectivity. Halvorsen points out Kierkegaard saw this pursuit of a detached universal perspective as a fatal error. Stripping the observer out of the equation doesn't produce perfect science. It creates a psychological trap that destroys the person trying to live inside it.
Kierkegaard illustrates this trap through the protagonist of Either-Or, a character identified simply as A. This character has actually achieved the Enlightenment ideal, observing his own life with perfect detached objectivity. But instead of finding clarity, A suffers from what Halvorsen calls a hypertrophied capacity for reflection. He overanalyzes every possible option from a completely neutral distance, which entirely paralyzes his ability to make a decision. This models his decision-making process. When viewed with total objectivity, every choice carries the exact same weight. If you step back far enough, everything simply is. Without a personal stake in the outcome, there is no logical reason to choose one path over another. Halvorsen traces this specific critique back to Kierkegaard's university teacher, Paul Martin Moller, who wrote a novel featuring a student similarly frozen by an overabundance of objective reflection. The attempt to view existence from a purely objective distance leads to a logical dead end. It produces total indecision, making it a failed framework for actually understanding how reality works. Kierkegaard diagnosed the Hegelian system, the attempt to map the entire universe through pure logic, as a kind of intellectual megalomania. It built a towering theoretical castle, but ignored the concrete reality of the human being living inside it. He argued that a complete, static system of existence is impossible to construct. Human beings are inescapable participants in reality, constantly striving, acting, and living in a state of becoming. He drew a sharp line between the what and the how. Objective science asks what the facts of a situation are. Subjectivity focuses on how the observer experiences and relates to those facts. You cannot simply edit the observer out of the observation. The act of existing anchors you to a specific point in time and space, inherently shaping the perspective you are trying to measure from. Any accurate description of reality has to account for the person doing the describing. Truth, in a lived sense, requires subjectivity. The critique of perfect objectivity soon migrated from theology into the hard sciences at the University of Copenhagen. Kierkegaard shared his ideas on the necessity of the subjective observer with his close friend and university professor, Rasmus Nielsen. Nielsen then taught these exact concepts within these lecture halls to his own student, a philosopher named Harl Høffding. Decades later, Høffding passed this philosophical framework to his own brilliant physics student, a young Niels Bohr. A 19th-century philosophical argument meant to cure existential dread became the foundational programming for one of the greatest minds in modern physics. By the early 20th century, empirical science hit an impenetrable wall. Classical Newtonian mechanics was failing. The entire framework had been built on that old Cartesian ideal, the assumption that a detached observer could measure an independent universe without interfering. In the subatomic realm, an electron might move predictably, but introducing a measurement, like bouncing a photon off it, violently scatters its trajectory. Bohr realized the flaw was assuming observer separation. The tool and particle form a single, inseparable system. The subatomic universe revealed a hard limit to the quest for pure detachment. At this scale, the dream of a completely objective measurement of physical data breaks down. Halvorsen refers to this breakthrough as Bohr's epistemological lesson of quantum theory, and it provided the solution to the crisis in modern physics. Bohr established a core principle. At the quantum level, the mere act of measuring a particle alters its state. The observer is a participant in creating the reality being measured. This quantum observer effect is a direct parallel to Kierkegaard's philosophy of subjectivity. They are the exact same realization applied to different fields. You cannot write the subject out of the equation. Kierkegaard is often categorized as a purely religious thinker, yet the historical lineage reveals he was tackling the conceptual problem that would eventually force physics to reconsider the role of the observer. Bohr's math and Kierkegaard's prose arrive at the same destination, an existence where the observer and the observed are inextricably entangled. For centuries, the universe was understood as a giant, predictable clockwork machine. If you knew the inputs, you could calculate the outputs. Cause and effect ruled physical reality with strict mechanical certainty. In the 1920s, the quantum revolution shattered this deterministic worldview. Scientists began to observe that at the subatomic level, particles ignored the predictable rules of classical physics. Wolfgang Pauli stood at the center of this upheaval. A brilliant theoretical physicist, he was one of the primary architects mapping the strange, non-classical behaviors of the electron. Pauli carried immense standing in the physics community. He was a regular at the Niels Bohr Institute in Copenhagen, a global hub for theoretical research, where Bohr's young son, Oj, affectionately knew the frequent visitor simply as Uncle Pauli. While Pauli mastered the mathematical structure of the physical universe, his internal world was in a state of collapse. Driven by severe emotional turmoil and a breakdown in his personal life, he sought professional help. This search for stability brought him to Zurich in the 1930s, to the practice of psychoanalyst Carl Jung. Pauli enrolled as a patient, hoping Jung's methods could untangle the psychic distress that his scientific mind could not solve. At the time, Jung was struggling with a theoretical crisis of his own. He had spent years observing meaningful coincidences in his patients' lives, events that seemed connected by significance rather than logic. Jung called this concept synchronicity. It described events like a patient dreaming of a rare golden scarab just as a real beetle tapped against the office window. However, Jung lacked a hard scientific framework to explain how these non-causal connections could actually exist. Pauli's arrival at the clinic provided the exact scientific framework Jung needed to articulate a reality where meaning, not just physical force, could act as a connecting principle. The analysis began with an intense focus on Pauli's dreams, which Jung used as a map to navigate the physicist's unconscious. One dream stood out. Pauli envisioned a massive world clock with multiple intersecting planes and colored rings rotating simultaneously. Jung viewed this clock as Pauli's unconscious mind attempting to visualize a grand cosmic order, a hidden symmetry underlying both the mind and the universe. This shared exploration of complex symbols dissolved the traditional boundary between doctor and patient, launching a deep intellectual partnership. To define this underlying order, Pauli began teaching Jung the bizarre, newly discovered laws of the quantum world. Pauli explained that at the subatomic level, these particles completely ignore the classical rules of space and time. He detailed wave-particle duality, the discovery that light and matter exist in contradictory states, behaving as both a solid particle and a wave of probability simultaneously. Most importantly, he described quantum acausality, the fact that physical phenomena can be interconnected without any direct causal link or physical force passing between them. Jung recognized that his collective unconscious, the shared reservoir of memories common to all humanity, functioned according to these same subatomic principles. The two realms showed a startling symmetry. The non-deterministic void beneath physical matter matched the non-deterministic void beneath the human mind. This realization led them to coin a single term for this unified reality, the Unus Mundus, or the unitary world. In the Unus Mundus, mind and matter are not separate domains, but inseparable elements of a single dynamic whole. Armed with Pauli's quantum insights, Jung finalized his theory of synchronicity for publication. He formally defined synchronicity as an acausal connecting principle, placing it alongside causality as a co-equal law of nature. Their work introduced the psychoid archetype, a factor that bridges the gap between the internal psyche and the external physical world. This shift moved the universe away from the dead mechanical clock of the past, framing it instead as a responsive continuum of meaning. Pauli's interest in these hidden connections persisted throughout his career, framing his later inquiries into the foundations of physics. The question of how distant elements of the universe communicate acausally was handed down to a new generation of scientists. In 1951, physicist David Bohm picked up the search for these hidden variables. Bohm formulated a version of EPR paradox involving correlated spins. He showed that particles could remain entangled, mirroring each other's states across vast distances without any direct physical links. The acausal connections Jung and Pauli debated in a 1930s clinic are today recognized as mathematical certainties in the study of quantum entanglement, proving to be structural elements of the physical world.
Neuroscience can map the brain's data processing with incredible precision, but it consistently hits a wall known as the hard problem. We can track electrical impulses moving through neural webs, but that doesn't explain why those impulses actually feel like something to the person experiencing them. Viewing the brain as a biological computer explains how we store memories or move our limbs, yet computation alone lacks a mechanism to conjure a subjective inner life. Seeking a more complete explanation, theoretical physicist David Bohm, a colleague of Einstein, began looking past classical mechanics toward a quantum description of reality. This visualization illustrates Bohm's theory of the implicate order. He argued that the distinct physical objects we perceive are just unfolded versions of a deeper enfolded whole, a reality where mind and matter are intertwined at the most basic level. In Bohm's framework, the brain acts as a localized site that accesses consciousness, which exists as a property of the universe itself. Moving from cosmic physics to the wet biology of the brain, neuroscientist Carl Pribram proposed a similar scale-invariant model called holonomic brain theory. Pribram discovered that memories are not stored in individual, localized neurons. Even after significant surgical damage to specific areas, his subjects retained complex information, suggesting it was distributed across the entire neural network. Pribram proposed the brain functions like a hologram. Instead of linear circuits, electrical activity in dendritic webs creates overlapping wave interference patterns. This structure means every part of the network contains the whole's information, maintaining function even after damage. While the theory explains how information is distributed, it ultimately lacks a specific trigger that could survive the warm, wet, and chaotic environment of human biology. A wave-based holographic model accounts for the distribution of thought, but it requires a physical site to inhabit within the cell. Dr. Stuart Hameroff took a different approach. As a clinical anesthesiologist, his career focused on the most reliable way to erase awareness. He realized that to understand how the brain produces consciousness, he first had to understand how anesthetics turn it off. Hameroff observed that anesthesia doesn't just stop neurons from firing, it specifically targets the patient's subjective experience. This suggested the root of awareness was deeper than the synaptic level, hidden further inside the cell. He turned to the work of Bohm and Pribram, validating their concept of non-local quantum waves flowing through brain structures rather than digital pulses. However, Hameroff noted our experience isn't a continuous, smooth flow. Perception appears to happen in discrete, strobe-like flashes, quantized moments of experience. This implies a physical threshold must exist, a point where the continuous quantum wave snaps into a discrete conscious event. Hameroff found the mechanism for that snap in the work of Sir Roger Penrose, a physicist who calculated the mathematical threshold for quantum collapse. Addressing the hard problem of consciousness now required linking an anesthesiologist's microscopic search with a Nobel laureate's equations of spacetime geometry. Penrose's theory of objective reduction focuses on the Planck scale, the most fundamental level of the universe. He looked at quantum superpositions, where particles exist in multiple states simultaneously. This diagram shows the core mechanic. A particle in superposition actually creates a separation in the fine-scale geometry of spacetime. It is as if reality is bending in two directions at once. These space-time separations are unstable. According to Penrose, when they reach a critical gravitational threshold, they spontaneously self-collapse into a single state.
Penrose argues that this specific physical collapse of space-time geometry is what creates a discrete moment of proto-consciousness. Hameroff identified the biological structures capable of hosting this process, microtubules. These are the protein skeletons inside our neurons, and the theory suggests they act as quantum computers to orchestrate these space-time collapses. This is orchestrated objective reduction, or Orch-OR, the point where the mathematics of space-time collapse translates into a conscious thought. To find the physical proof, we have to zoom into the microscopic interior of a single microtubule. Microtubules are built from tubulin proteins, which contain aromatic rings. These rings create nonpolar resonance clouds that naturally exclude water. This environment forms a quantum underground. It acts as a biological shield, protecting delicate quantum states from the warm and noisy surroundings of the brain. As shown here, this shielded quantum underground is the specific site where anesthetic gases bind. They physically interrupt the quantum resonance, which halts the conscious process. This evidence suggests the brain is not a cold algorithm or a biological hard drive. We are instead observing a form of entanglement with the cosmos. Our brains function as quantum orchestras, tuned to the resonant frequencies of the universe.